Welcome. In this presentation, I'm going to talk to you about Raman spectroscopy and give you a basic tutorial of the technique itself. This is not about the experimental technique itself, it's more about the fundamental principles that govern Raman spectroscopy. So there are two parts in this presentation. So the first part is going to be this recording, and I'm going to talk about general principles. And in the part two, I'm going to talk about applications, and mostly in 2D material. So the objective of this talk are as follows. In the first part, so this presentation, I'd like the attendee to understand what Raman spectroscopy is, understand the information that you can get from it, and being able to read the Raman spectrum. In the second part, so in a different recording, I will talk about Raman spectroscopy for low-dimensional materials, mostly two-dimensional materials in fact, and then discuss tip-enhanced Raman spectroscopy briefly. So this is about a primer, Raman a primer. So if you do Raman, you are going to use an experimental setup like this. It looks a little bit complicated, but it's actually not that complicated. We start from the left. So we have a laser. It's important. We will see why we need a laser, because it's a monochromatic light and coherent. The laser, we shine a laser on a sample. So it's here, look like a chemical bottle here. Then there is scattered light that then goes through a focusing lens, and then after that there is a spectrometer here that allows to separate the different frequencies of the scattered light, and a CCD detector count how much of each frequency is scattered by the system. So this is really what's happening. So what we want to understand is what are the principles that lead to different frequencies being recorded at the outcome in the CCD detector. So an experimental image would look, an experimental apparatus would look something like this. This is now tabletop. Of course, you can also have Raman within another experiment, but this would be a tabletop system that you would use. So if you look at the Raman spectrum, I just pick here pretty much a random one. This is the spectrum of SiO2. And when you look at the spectrum of Raman, you have such a plot, and the x-axis we usually call the Raman shift. I attract your attention that to the fact that the units I usually use centimeter-1. I'm going to discuss that in a second in the next slide. The typical range of frequencies, so in wave numbers, centimeter-1, are in the hundreds to a couple of thousand. And on the y-axis, you have the intensity. So in this example, for example, if we use a laser light, we shine it on SiO2, and the outcome is that we have a number of Raman shift recorded at those frequencies with sharp peaks, which we will see correspond to intrinsic properties of the material. So before we move on, let's remind about a little reminder about units, because as you know, different fields use different units. They all usually correspond to frequencies, but of course we use the units that are the most logical, or the most in the sense of being in the right range of numbers for the particular technique. So let's remind about units. The information we receive is in a function of frequency. As we will discuss, in fact, those frequencies correspond to a vibration of the material. As we know, if we look at the SI unit, so the International System Unit, the frequencies are usually expressed in hertz, so 1 per second. But it can also be expressed in wave number. So you know, of course, the wave number is the number of waves that you have per centimeter, right? So you can see that in the picture on the right-hand side. You can talk about frequencies, which is in this case 2.5 per meter. So the frequency we have here. But the thing is, we can also count how many waves we have for a given centimeter, and that's what we find here. Okay, so that's nice. This is important to know. You might see some data that are given in terahertz, so 10 to the power 12. This is not unusual because terahertz actually correspond to the same range as wave number, more or less. I think there's a factor of 33 between the two. But chemists and physicists and material scientists usually use wave numbers, but it's not unusual to see terahertz. So the frequency is also energy, of course. We know from the Planck relationship that frequencies and energies can be converted from one to the other. So you sometimes even people use milli eV for this kind of for the x-axis. So do not be surprised if you see that in the Raman spectrum. And here is a simple conversion table. So in Raman we are usually in the thousands wave numbers, 1000 centimeter minus 1. So again, that means that there is 1000 waves per centimeter, and that corresponds to 124 millieV and 0.3 terahertz. So all these units are fine. Just don't be fooled by what you use. Okay. Now the next question is that we use a laser and then we shine the laser on the material. So the question is, why do you use a laser? Well, we use a laser because we need a monochromatic light. Of course, a monochromatic light means that there is a single frequency present in the incoming light. This is going to become very clear very soon, but of course, since we are analyzing the frequency response of the material, we don't want to make things complicated, so we want to simplify by just using one single frequency in the income. I will say also that measurement can be made with different laser light. Typically people use red, green, and blue light, but you can use different frequencies, and actually those are usually very finely tuned. The most important thing really for this tutorial here is to remember that light is also an electromagnetic wave. And if it's an electromagnetic wave, it means that it has a magnetic field and an electric field. In this case, we are not going to worry about the magnetic field because we do not have a strong coupling between magnetic field and the material, at least for what we are looking at here. But the electric field matters. The electric field is going to interact with the material, and this is this electric field interaction with the material that really matters here. So when we really say that there is interaction between light and the material, we really mean that there is an interaction between the electric field and light. So it's good to remember, of course, for example, a plane wave here. If it goes in the direction k, which in this case is the x direction on this plot, we see that we have oscillating magnetic field shown in red and an oscillating electric field shown in cyan color. This oscillating field is oscillating exactly at the frequency of the laser. Okay, so that's really what matters. So we do basically have a time-dependent electric field that is impinging on the material. And the question is, how does the material respond to this? So what can happen when we shine a light on a molecular material? So let's try to go back to some basic before we talk about Raman scattering. What can happen is something like this. So you have a piece of material shown with the gray bar, and you have light coming in from the left. So of course you can have reflection. This is not something we're interested in. You can have transmission. This is not something we are interested in either. You can have absorption of light, and this absorption of light can actually then be used, for example, for PL measurement, so photoluminescence measurement. We are not interested in that one. But we also have scattering. Scattering will be this interaction between the light and the material, and the light basically gets in and interacts and then gets out. And what we are interested in Raman spectroscopy is to analyze the scattering light as it goes out. Okay? So this is what we usually do. If we have a material that is very, very highly reflective, Raman spectroscopy is complicated because, of course, most of the light is reflected, and clearly we do not have a strong Raman spectrum. So this is something to remember as well. So what can happen when we shine light on a material? So here the material is going to be very simplified by this sphere, by this disk. And what we do when we have a laser light that we shine on this material, we have an electric field which is a vector, of course, with a direction E. As we know, if it's a material, it has electrons in it, and the material, according to Maxwell's equation, is going to rearrange the charges in such a way, like this, in such a way that the dipole moment inside the material counteract as much as possible the electric field. So basically the material always tries to minimize the internal electric field. And the total electric field, of course, is the sum of the electric field due to the dipole that's induced by the electric field and the electric field itself. Okay, so this is something that we are well familiar with. And of course, there is a relationship between the dipole moment, mu, and the electric field. And that relationship is given by this equation in yellow. So we have on the left the dipole moment, and on the right we have the electric field, and the proportionality value here, chi, is called the polarizability tensor. I like to insist on tensor, of course, when we look at this in a very fundamental courses, maybe in first year course or something like that. We usually use that as a scalar. But the reality is that it's a tensor, and I'm going to explain that to you why in the next slide, but just suffice to say that if chi was a scalar, we would say that we would assume that the dipole moment and the electric field are aligned, which is not necessarily the case. I'm going to explain to you in a cartoon next. But if the system is uniform and isotropic, chi is indeed like a scalar, and to be like a scalar, that means that the tensor is proportional to the identity tensor, and that would be something like this, something like this that you see on the screen, where the three values on the diagonal are the same. So that would be only true for uniform and isotropic material, which is of course not very often the case in reality. For example, a molecule is neither uniform nor isotropic most of the time, I would say all the time. Okay, so let's try to have a look at a system that's not isotropic and uniform. So let's suppose that you have something here that doesn't look like a disk anymore. And there is some gradient. I don't know if you see this on the screen, but there is a gradient of color as well, which means that the material is not uniform in its composition. If you apply an electric field again, same way, so the field comes from the laser light from Raman, you also have a reorganization of the charges, but in this case, the dipole moment linking the cloud of positive charges and the cloud of negative charges is no longer horizontal. In fact, it's roughly the way I plot it here on the screen. And if you go back to this relationship that we had before, then the polarizability tensor would look something like this. Okay? It would look something like this. It's no longer diagonal, and we have different elements. So these properties, chi, the chi is a property that's intrinsic to the material. It's how the material responds to an external electric field. So this is actually important to do this, because understanding this effect, if you understand this, what I just explained, you are basically halfway through understanding what's happening in Raman spectroscopy. Okay, now, Raman spectroscopy in particular interrogates the vibrational properties of the material. So the question that we can ask is, how does the polarizability change when we excite a vibrational normal mode? So let's try to take a second here to understand the question. We imagine that the material is going to be excited with some, excited in the sense that some energy is going to be imparted to the material, and the material will respond by having atom vibrating. Okay? So the vibrations that we are going to have will be a composition of vibrational normal mode. So the normal mode as the intrinsic vibration of a material. Okay, now let's go back to the equation that I showed before. Now, just to make it a little bit clearer, I put 2 bars on chi to remind you that chi is indeed a tensor. It's not just a scalar. It's important to know. So what we have an electric field. And the electric field is a vibrating electric field, oscillating. It's an oscillating electric field, simply because it comes from light, and light is an oscillating wave. And it's, in this case, the way I wrote it here, it has a single frequency omega naught. So omega naught is this monochromatic light frequency that I mentioned before. So we could use more than one light if we wanted to. We would have a sum, but it would make things a little bit more complicated. So here we suppose that we have light at a light at frequency omega naught impinging on the material shown by the blue bar. Okay, now imagine that the effect is to also excite vibrations on the material. And the question we can ask ourselves is, if we have a vibration in the material, how does the dielectric tensor change? And of course, in this case, we suppose the vibration is, of course, we are going to work with low amplitude vibration, so the energy imparted is not very large. So we can use Taylor expansion to first order. So this is the Taylor expansion of the object chi. And of course, we can do that for small displacement, right? It's Taylor series at first order. First order means that I drop everything that's shown by the dots. And what we see is that, of course, the chi, once we have a vibration, will be the chi when there's no vibration. So Q equals 0. Q in this case means no phonons, no vibration of no normal mode of phonons, plus a correction that's linear with the phonon and also depends on the first derivative of the dielectric tensor with respect to the phonon. So again, all you need to know here is some simple differential equations and maybe tensor algebra, but very little, really. All you need to really realize is use Taylor series. So what's in the gray box is basically telling you how the dielectric tensor has changed once we have a vibration in the material. And of course, we know that the Q is a vibration of the material, and it's going to be a normal mode. Normal mode means the vibration has a single frequency. And again, in this case, I wrote that frequency of vibration omega m. So this corresponds to an oscillation of the atoms in the material. And then we can obtain those vibrations using different techniques, different methods, but it corresponds to a vibration. Now, this is pretty nice because we are going to introduce all we know in the green box, the orange box, and the gray box back into the red box, okay? And so we are going to find something like this. So the dipole moment is going to be equal to chi, which is, I replace chi by what I have in the gray box here. This is going to be this. So we have chi. This is what we have in the gray box. But we also have a q here. So I'm going to replace the q by what I have in the yellow box right here. And then E, I'm going to replace it by the oscillating value. So I think this is pretty straightforward to see this. This is an equation that we have. So really, this is a classical approach, really. This is not the full quantum mechanical approach, but this is a classical approach that tells you how the dipole moment is actually changing when we have an oscillating electric field and also in the presence of a vibration in the material, okay? So we have this equation. I'm going to reproduce it on the next slide because it's an important one. And what we need to do now is to do a little bit of trigonometry. And in fact, if you are familiar with doing some of those fundamental equations, when you have two cosine, you have a cosine times another cosine, you should have almost a Pavlovian-like reaction to use this equation for the product of cosine, where you can replace the product of cosine as the sum of the cosine of the addition and subtraction of the argument. Okay, this is a basic equation in trigonometry. Now I do that, and I'm going to replace the cosine by this value, and I can rewrite now mu this way. Looks like a difficult equation, but it's really not. Actually, I even invite you to pause the screencast for 5 seconds to convince yourself how you go from the first equation to the last. But the point is, we can now write things like this. Now, this is actually all we need to know the basics of Raman spectroscopy. Let me explain to you why on the next equation. So we have this equation here. This is the same as the last one on the previous slide. Now imagine you have a molecule. Here I just use CO2, but it doesn't matter. I just use that for illustration purposes. We have an impinging light at omega naught. Remember, this is the frequency of light. So this is the frequency at which the electric field oscillates from the laser light. Okay, good. So you see that we have on the equation on the top 3 terms. We have the first term here that's going to oscillate at omega naught. And this is actually a scattering. This is called Rayleigh scattering. And the Rayleigh scattering happens at the same frequency. While you see the response to mu is oscillating at frequency omega naught. So Rayleigh scattering is what we use to show why the sky is blue. We aren't going to worry about this one. This is the Rayleigh light. This is essentially a response of the material that's basically no response. The frequency that is impinging is the same frequency that comes out. We do not get much information from the Rayleigh light in Raman. In fact, we don't get any. In fact, it's in the waves because it's usually the largest proportion of the scattering is through the Rayleigh line, and it's usually a pretty large signal that we mostly try to get rid of. But let's look at the other two. So this corresponds to something like this. In Rayleigh, you have these are the different states that we have in the material. We have absorption at omega naught, and you have scattering at omega naught. It's called elastic because there is no exchange of energy. Good. Now the next term is much more interesting. The next term, which corresponds to a vibration at omega naught minus omega m, is usually called the Stokes line, the Stokes scattering, and this corresponds to the emission of light that's actually at omega naught minus omega m. Now I have to tell you right away that the frequencies of vibration omega m, the frequency is much smaller than the frequency of, for example, a red laser or green or blue laser. So this means that this signal here in the cyan line is indeed non-elastic because you have absorption of energy of some energy corresponding to the vibration, but the difference is not that big. So, but there is a difference, but it's not very large. Okay. If we look at the band diagram, we can understand the Stokes effect. In the Stokes effect, you start from the nu equals 0 state, which is the state of the material, of the molecule. The molecule absorbs h nu 0 or h omega 0, h bar omega 0, and then there is there is a relaxation. So basically, the material goes down in energy, but instead of going back to the fundamental nu equals 0, it goes to v equals 0. It goes to the vibration v equal 1. So in other words, the material during the relaxation, the radiative relaxation, you have the emission of phonons at frequency omega naught minus omega m. I'm sorry, the labels here are not the same, but nu 0 minus nu vib correspond to omega 0 minus omega m on the screen. But the point is, it leaves the material in an excited state of vibration. So basically, the material is now vibrating at frequency omega m. Now there is another term on the right-hand side. This is this term, where now the oscillation is higher. So this is a little bit weird, right? That basically the light coming out now is at a slightly higher frequencies. And the way to explain this is that your material was initially in an excited vibrational state. So it was initially in a vibrational state. The material picks up the energy, the energy h bar omega 0, and then relaxed all the way to the ground state. So in other words, what light did, light essentially picked up the vibration and removed the vibration from the material. This is called the anti-Stokes. So you would have, this is a very interesting thing because of course you can have vibrations simply due to the equipartition theorem at finite temperature. So the anti-Stokes would actually be able to pick up that. Now it's interesting to see that usually the anti-Stokes and Stokes signal are symmetrical, but you can also use the difference between anti-Stokes and Stokes as a thermometer. But we are not, simply because, of course, the intensity of the anti-Stokes line will be related to temperature, of course, because that depends on how many vibrations exist in the material. But do not worry too much about this. We are not going to talk too much about the anti-Stokes here, but know that if you have to do Raman spectroscopy, you will have a Stokes and an anti-Stokes. One will pick up a vibration that's anti-Stokes, and not the other one, Stokes, will actually leave vibrations behind. Okay, so I think it's very nice. Now this technique was first thought by Raman many years ago, many decades ago, and this is why it bears its name. Okay, so this is basically how Raman spectroscopy works. This is an important slide to understand, and this is all based, I have to say, that it's all based on a classical description of interaction between light and the material. But what matters really is this technique interrogate the vibrations of the material. And the vibrations of the material, of course, are intrinsic properties of the material. Therefore, we can measure properties. Now, what's interesting is that you're going to have peaks as those different frequencies, omega naught minus omega m, for example. But you know omega naught, because omega naught is really what you entered. Now, if you look at the shift between the incoming at omega naught and the output omega naught minus omega m, the shift is omega m. And this is why we if you remember the first Raman spectrum that I showed you, we had a Raman shift. So what we really report on those plots are omega m, which are directly related to vibration of the material. So this is really nice, I think. Okay, so the take home for the rest of this talk is that we can calculate, we have a Raman intensity that depends on this first derivative of the dielectric tensor as a function of with respect to a vibrational mode. Now, this equation is a little bit more complicated than the one I showed you before, simply because I actually explicitly wrote the vibrational mode as a function of the coordinates. So as a function of the coordinates in Cartesian coordinates. But this is just a transformation of, this is just using the definition of normal mode. So do not worry too much about this equation. The point is that we can express, of course, the normal mode either using the normal mode coordinates or the Cartesian coordinates, as I've done here. Now, the Raman intensity is going to be directly proportional to the probability amplitude will be dependent on this alpha, of course, and the intensity will be dependent on the square. Now, what you see, if you have a tensor here, what matters is really also to do a dot product with the incoming light, which is right here, and then the outgoing light, GS. This is very important because GS and GI are actually the polarization. So I have to explain this a little bit. Since alpha is a tensor, we need the intensity being a scalar, we need to be able to reduce that to a scalar. And the way to do that is to do a dot product with two vectors. And the two vectors, GS and GI, correspond to the direction of the light. So let me show that to you on a cartoon. So we have the sample, we have the incoming light with a wave vector Ki. Remember, K is the direction of propagation. The polarization, in other words, the direction of the electric field is perpendicular to that line, is going to be given by GI. It's right here, it's the GI. So the polarization, the direction of the electric field. And then the outgoing light is going to be at Ks, the scattered light, with a polarization GS. Now, experimentally, of course, you do have scattering at different GS, but the polarizer, the experimentally, you actually pick a given polarization. So very often you might see in the literature that we can do studies where you keep the GI the same, so the incoming polarization, but you change the polarization that you actually measure. And you can get more information about your material by varying GS. And you can understand that easily from the equation in the box, because of course the dot product between GS and alpha will interrogate different elements of alpha depending on the value of GS. And of course, the different value in alpha, remember this the tensor, the matrix element of the tensor, are going to be different depending on the material, but also will be intrinsic property of the material. So we can actually learn a lot about doing a polarized Raman spectroscopy. Good. So to summarize what we've done so far, Raman spectroscopy is based on how we can measure how the excitation source induce change in the electric dipole. So I really need to analyze, to insist a lot. What matters here is the change in electric dipole. It is not the fact that there is an electric dipole. So there is another technique that's called infrared spectroscopy, which I'm not covering here, where infrared spectroscopy interrogates the presence of a dipole. Raman spectroscopy interrogates the change in an electric dipole. And if you remember, the change comes from the fact that we calculate the first derivative of the dielectric tensor with respect to a normal mode. Okay, so it's the derivative. So what matters is the change in the electric dipole. Nice. Now, what we hear a lot is that Raman has a set of selection rules. And all we need to understand that is to look into those equations here on the top right that we already introduced before. So basically the selection rules go as follows. If a vibration results in a change in the molecular polarizability, again, that's what I said, if it leads to a non-zero first derivative of chi, the mode is potentially Raman active. Okay? Now, here is where the selection rule come about. The change in the polarizability can only happen if we have specific symmetries in the material. And this is actually easy to understand, because if we have a symmetry that does not allow to create a dipole moment or to change a dipole moment in certain directions, simply because the atoms are arranged in such a way that there is no change in dipole moment, then in that case we do not have Raman intensity. Let me tell you an example. Suppose that you have a molecule, like, let's suppose you have H2. If you have H2, if you have the two atoms that are moving along, that are just stretching, if we are stretching the bond, we do not find a change in the polarizability. In that case, we would not have a Raman active mode. So the symmetry matters a lot, and it turns out that the good news for you is that you do not have to worry too much about that, because all you have to do is to find the space group and the point group symmetry of the material. And the reason why you don't have to worry about that is because Raman spectroscopy is so important that the character table, so those tables that describe the point groups, will actually tell you which mode are Raman active due to symmetry. So what you need to do Raman is to understand a little bit about what character tables are for symmetries. Of course, this short screencast is not going to include that. It's just it should be another screencast altogether. But the point is, the Raman intensity can be not the Raman intensity, but the Raman activity can be obtained from the character table, and I'm going to show that in 2 or 3 examples just to be clear. It turns out that to be Raman active, a certain representation of a vibration, for example, has to transform like a binary product, like xy, yz, xz, x square, y square, z square, and that way the reason for that is, of course, because the first derivative of the dipole has to be non-zero. Just I try to give you a hand-waving argument for this. Dipole, if you remember, dipole moment between two charges depends on the distance between them, right? Between the two charges. And of course, if the dipole is just linear, then if it's a linear system like this, the variation is not going to allow you to have a Raman active mode. So in order for the derivative to be non-zero, you need to have a quadratic term, basically x squared, y squared, z squared. So this is if you are not familiar with character table, it's a little bit nebulous for sure, but at least bear with me, and I will show you at least in practice how you can get away with this. So let's have a look at an example. And for that I use methanol. So we have we have oxygen in red, carbon in green, and all the other gray atoms are hydrogen. If you look at the space group symmetry, and in fact the point group symmetry is a CS point group. It has a little bit of symmetry, but not much. And if you look at the character table in books or on the internet, you will find that there are two irreducible representations, A prime and A prime prime. The vibration of your material will also be classified using the same irreducible representation. Sorry. Now, what's nice is that if you look into this, you will find that there is a column that's going to say quadratic. And quadratic will tell you which of those modes behave quadratically. And it turns out for methanol, both the mode A prime and A prime prime correspond to quadratic terms, and therefore they are Raman active. So on the right-hand side, so you do expect those modes to be Raman active. So on the right-hand side, I'm showing you all the vibrations of methanol. Again, if you are interested, just pause this screencast and look at them more carefully. I'm not going to go in details, but in principle, we should be able to see all those vibrations and different frequencies in the Raman spectrum. And this is the Raman spectrum of methanol. And you can see that indeed all those vibrations are visible in infrared. Actually, they are also visible in infrared, it turns out, but they are visible in Raman. Sometimes they are not reported, like in the table on the right-hand side, simply because the intensity is too low. But all those vibrations, they are allowed, but sometimes it turns out that the change is small. It is not zero by symmetry, but it is small, so we don't see it. So in other words, if you measure the Raman spectrum of methanol, you will see all the vibrational mode frequency here. Again, I remind you, the x-axis is Raman shift in wave numbers. Here the values are a little bit larger than what I reported below. It's around 3000, simply because the atoms that are involved are light. So hydrogen, for example, vibrations of hydrogen. If you have a light atom, of course, you have a much higher frequency vibration. Now there is another example, which would be ethanol. So you add a C2 in this. So this is ethanol. Ethanol actually has very little symmetry. It's C1 point group. And of course, they behave like the identity, therefore they are also all quadratic. So all the mode of ethanol are visible in Raman. And what's really the strength of Raman is to be able to see, if you're given a solution, you can tell if you have ethanol and methanol, because if you compare the spectrum, you see that indeed the spectrum are slightly different, even though there is a lot of similarity between the two molecules, but there are well-marked differences between methanol on the bottom and ethanol on the top. And Raman spectroscopy, which is a cheap and fast technique and does not destroy your material, that Raman spectroscopy can actually tell you if you have methanol or ethanol, or if you have both, in fact. So this is basically what I wanted to tell you here about the introduction, about the classical part of Raman. And what matters is that the peak positions gives you a chemical fingerprint. So you are able to tell which material you have, because each material has a well-defined set of vibrations. Okay, so good. So I'm going to tell you a little bit more about phonons now. So we are talking about vibrations, phonons, and it's impossible to do Raman spectroscopy if you don't have a basic understanding of phonon. A phonon is a collective excitation in a periodic arrangement of atom and molecule. So it's a little bit like if you have atoms in a material, you are going to have a collective vibration, a collective excitation of the ions, and the vibrations are actually responsible for the sound propagation, or at least the acoustic phonons are. You also have optical phonons, which actually are those that are not acoustic phonons. Basically, the optical phonons, there is an example shown on the right. And I'd like to take a second here, and why do we call them optical phonons? It turns out that if you look on the right-hand side, you see that the vibration, so the bottom one, the bottom plot on the, shows that there is actually a creation of a dipole moment there, a change in dipole moment as you have a vibration. The reason for this is that every other atom is vibrating out of phase. So when you have a minus goes up, a plus goes down, and so on and so forth. In other words, you have a creation of a dipole moment, and in fact even a change in dipole moment, and therefore if you have a dipole moment or a change dipole moment, you can interact with an electric field. And this is if you, since in optics you have, optics or light, you have an electric field, as I reminded you 20 minutes ago, this kind of vibration can couple with light. So can couple with light, and therefore that's why they're called optical phonons. The acoustic phonons are those that do not couple with light, so you will not see them in Raman, but they actually are responsible for sound propagation. Okay? So very often for phonons we can do something very simple to understand phonons, and we can calculate them using quantum mechanical approaches or classical approaches. But let me give you a rough idea of what we mean by that. So phonons and vibrations, here I use them interchangeably, even though we usually call vibrations in a finite system like a molecule and phonons in a solid. So in the second part, in the second screencast where I will have applications, I will talk mostly about phonons instead of molecular vibrations. Anyways, the way we can think about this very simple molecule, it's a CO, is, for example, we can think about it as being two masses that are connected to a spring. And the spring has a force constant K, and this force constant corresponds to the strength of the bond between the two materials. So we can introduce the mass of the ions, or the atoms, and also the force constant, that's description of the bond. Of course, we know that we have this kind of thing. We can calculate the vibration of this. This is a freshman level type of calculations. But we can go further than that. We can look at like a solid like this one. I hope you can see this is a cubic solid. And we can actually replace also all the atom by some kind of balls and the bonds by springs, and get all sort of arrangement of springs. And then we can calculate all the vibration of those material as the all the normal modes, the vibrations, by calculating, by basically writing the Newton's equation for these complicated systems. And then we end up with all the normal mode of the system. Now we very often work in the harmonic approximation, and the harmonic approximation simply means that the interaction, we suppose that we have a simple quadratic term, so basically Hooke's law, a simple linear spring in this. We can also go beyond, of course, harmonic approximation. We can go anharmonic approximation, but that is a little bit beyond the scope of this basic introduction to Raman. So we can calculate phonons. I could skip this slide, but I'm going to show it to you because most of what I will show you in the applications, I use this technique. This technique simply corresponds to calculate the dynamical matrix by basically calculating all the bonds and the force constant, and by diagonalizing the dynamical matrix, we end up with all the normal modes. So, but do not be too concerned about this slide, other than the fact that we can, this is basically the way we calculate the phonons in solid. Okay, for example, a technique we use a lot is density functional theory. We love to do DFT for everything, so quantum-based calculations, but we cannot always do it simply because those calculations can be very expensive. If you like DFT, there are a couple of presentations in this YouTube channel that you can follow as well. Okay, now before I conclude this first part of this first screencast, I'd like to tell you a little bit that what we've done so far, describing the Raman effect, was really a classical approach, right? We considered the electric field, considered the dipole. All this is pretty much classical electrodynamics. I have to tell you give you a couple of words about the quantum theory, just to be clear that It's a little bit more complicated when you look at very subtle effects, but that's why it's important for me to explain to you. In the quantum theory, we are going to show a bit more equations, but again, basic quantum mechanical equations. And everything is based on the time-dependent perturbation theory. So if you had to remember to remember one thing from what I'm going to tell you in the next few minutes, is the fact that if you have a particular system, a solid or a molecule, you can study its electronic properties, its quantum mechanical properties, and you can look at an external electric field as a perturbation. Now, since our electric field comes from a laser, it is an oscillating electric field, therefore it's a time-dependent electric field, and we are going to look at this electric field as a perturbation to the system. So we need to use a time-dependent perturbation theory to do this. So now I'm going to tell you the same with equation. We have the electronic system, so basically the molecule, for instance, or the solid, that's described by this Schrödinger equation, time-independent Schrödinger equation, that gives you for the vibrations, right? We recognize here in the Dirac notation. We know the time evolution, of course, of those states, so of those vibrations, because the Hamiltonian is not time-dependent, therefore the time evolution is simply given by a phase factor, so to speak, that comes from the exponential, that simply comes from the fact that the Hamiltonian is not time-dependent. Now the perturbation to the system corresponds to adding a potential V of t, so a potential time-dependent potential, and that potential, of course, oscillates at the vibrational frequencies of the laser. So here I wrote it omega v as the frequency of the external potential that corresponds to omega naught in the beginning of this presentation. Now we have the time-dependent Schrödinger equation now that we have to solve because we can no longer use the exponential, simply the exponential factor that I use on the top right, since we do have a time-dependent Hamiltonian. So we do have to solve this time-dependent Schrödinger equation to find how the state of the system in the presence of an electric field how it changes as a function of time. Now the way it's always done in time-dependent perturbation theory is to expand the solution on the basis of the state before we have a perturbation. Right? So we suppose that all the states that we have before the perturbation, so the one from the first line, correspond to a complete basis, and therefore we can write any solution as a linear combination of those elements of the complete basis. Now the difficulty, of course, is to try to find the coefficient an of t, and this is time-dependent perturbation theory. And again, our best friend as physicists is to use Taylor series, and we suppose that those values are going to depend on first order, zeroth order, first order, second order, and so on and so forth. And we are going to chop the Taylor series at some place where we can, until we cannot calculate it anymore. So let me just give you a few more slides here on this. This is basically what we're looking for. So the expansion of the solution on the basis of the eigenstate of the non-perturbed Hamiltonian. And the potential, of course, is going to depend on the number of interaction that we have, corresponding to the light, to the vibration, and so on and so forth. And we can actually calculate those terms simply by introducing this into the Schrödinger equation. And we end up with equations that are pretty ugly, I have to say. And they look like this. So please do not stop, do not log off YouTube just yet. These are ugly equations. I have to show them to you because we have to implement them. And this is where we are happy that we have those perturbation, time-dependent perturbation can be written in terms of Feynman diagrams. So all those 6 terms that we have on the bottom right correspond to six diagrams, 6 Feynman diagrams that we have, which correspond, which include 3 types of particles. And this is why we need to go to third order. Third order, we have 3 types of particles. The first particle is the incoming light, omega L. The second one is the outgoing light omega s. And this third particle is the vibration omega v. Now, in this Feynman diagram, we see that the wiggly lines correspond to phonons. No, I'm sorry. The wiggly lines correspond to photons. The zigzag line correspond to phonon. And the double arrows, horizontal arrows, correspond to interactions. So this is a way to summarize the 6 terms that we have before. Just to go a little bit more in detail, before I move on, I'm going to tell you the important message, of course, here is that in this case, at the end of the day, we have conservation of energy. So the frequency, so the Raman shift omega nu has to be equal to the difference between the outgoing light and the incoming light. Good. Let me explain to you one of the 6 processes, in fact, one of the most important processes that we have. So this is actually the electronic state that we have. We have this electronic, I just put 3 states here. The initial omega I, which is the ground state, omega n, and omega m. So these are the electronic state before interaction. Now the system is going to absorb light. It absorbs light, and as a result, now the system absorbs light. As a result, we have a transition from an electron from the ground state to some excited state. So the electron is excited to a higher value, and we have the formation of an exciton. So an exciton is basically a pair of hole and electron. So this is what we have. This is the quantum mechanical effect. Now this electron can relax into a vibrational mode, for example, and you have to a lower energy. In this case, the energy corresponding to the presence of a phonon. And in this case, you have, during the relaxation, it's a radiative relaxation, and you have the emission of a phonon in yellow. And finally, the system doesn't like to be in an excited state and then relax completely back to the ground state. And in this case, the energy that's the omega s, it corresponds to a photon. Okay, so this is basically what's happening. This is the quantum mechanical description of what I described before. So of course this is compatible, but this is actually the correct way to do it. Now I can do this again, but now I'm going to draw the Feynman diagram for you. You start from a system there. So I showed it. I'm representing it with a white dot. You have an incoming light. This incoming light has an interaction with an exciton. Right here, the exciton is represented by the double line. This is the interaction. This system relaxes and actually emits a phonon in yellow. And then of course you still have the exciton between epsilon and epsilon I. And at the end of the day, you have yet another emission omega s. So you were not probably expecting to understand the Feynman diagram by following this screencast, but here we go. So we have conservation laws, of course, as I said, important conservation law. Omega nu is equal to omega L minus omega S. Omega nu is the frequency of the phonon. This is what we call a Raman shift, because it's a shift. What we measure is the shift between the frequency that's incoming, omega L, and the energy and the light that's outgoing, omega S. So S is for scattering, L is for laser. Now there is another conservation law that's actually very important, and in fact it's very interesting for all of us, makes our life easier, is the conservation of momentum, and I need to explain that in a little bit more detail here. As you know, there is in this process, there is extremely little momentum exchange in the process, simply because the values of the momenta are so different that there is very little chance there is very little possibility to exchange momentum. And so the most likely in this one phonon process, in order for the momentum to be conserved, the only way is to make sure the momentum of the phonon is zero. So if you're familiar with a phonon band structure that corresponds to the gamma point of the band structure, of the phonon band structure. And so in first order, and when we say first order, we mean when only one phonon is involved. So even though the perturbation theory is third order because we have 3 particles, we usually say Raman first order when there is only one phonon, like here. In this case, when we have only one phonon, the momentum the only way to excite a phonon is to excite it at the gamma point where q equals 0. Okay, so I hope it's clear. So the last slide of this first part will be here, is that we can calculate the intensity of Raman spectroscopy. So basically on the bottom right, I also reminded you the polarization setup. It's very important, something that sometimes students have some difficulties with, but I hope this slide is helpful. And we will have Raman activity if we have if the derivative of the polarizability is non-zero, as shown in the equation on the top right. We can actually look at the character tables, which correspond to the symmetry of the system, to tell which mode will be Raman active. I hope this screencast was useful to you, and if so, come back for the second tutorial, the second part of the tutorial, and maybe check out the other recordings as well in this channel. Thank you very much.